So let's suppose you have some data of an object in space. Maybe it's something like a missile that's flying through the air, and you know where its location is on the Earth at each time update. So maybe you get updated 100 times a second even, and you're finding out where it's at and its XYZ location. Well, if we were to plot that on a 3D axis, so like we have here, some trajectory, we could at each time step determine the X, Y, and Z location. And that would be, you could think of that as a space curve. The trajectory would be called a space curve. The locations, we could plot each of the axes direction. We could plot its X, Y, or Z location as a function of time. Basically, at any given time point, we can figure out what the Z value is or what the X value is. And then we could take each of those individual components as functions of time and set them up as components of a vector, R of t. And so the idea of a space curve is to take those functions that describe the position on each of the standard axes and represent them as components there. So why am I saying that? Well, the reason I'm saying that is because sometimes we have data, we have these X, Y, and Z points, and what we want to do is we want to develop functions that describe how this thing behaves. So this is a very common scenario in simulation planning, or even in the field of like computer software, developing predictive models, right? We have data of what has happened, and we want to develop functions that describe what something looks like in general. So I say that because there's any number of ways. If all you have is just some graph, and you don't necessarily know information about how it moves, which isn't that common, but you may have anyway. If you have some graph, you may not know the best way to approach that. And so for a space curve, it can be described by multiple functions. So I'm going to show that we have this R1, R2, and R3 of t. And each of them are sums of sines and cosines. And I want to show you that even though those are different functions, they would make the same graph. And I'm bringing that up because as you go along, what you'll realize is there's so many ways to describe the same thing. So let's plot this out. So I have this space curve, and at time equals 0, so again, t doesn't have to be time, but so often it actually is. When t is 0, this is 0, and we start at j. So we start up here. Now, when we make it all the way to pi over, I'm sorry, yeah, you're right, I'm sorry. As time moves along, as we move along in time to pi over 2, so again, in this particular case, that's not the angle on the graph, it's just some sort of time index. As we move to pi over 2, we go to I. So we go from here in this direction to I. And then when the time index moves forward again to pi, we make it down to negative j. And then as the time index moves to 3 pi over 2, we make it to negative I. So what we see is that this, as time moves forward, is going in a clockwise motion. Clockwise motion to construct the graph of that circle. But that's not the only way to construct the graph of that circle. If I took this function, cosine ti plus sine tj, at the starting time, at time 0, we actually start at I. So let me make some adjustments here. So this is time 0, pi over 2, pi, 3 pi over 2. But here, on this one, we start at I at time 0. And then by the time we get to pi over 2, we've made it up to j. And then by the time we make it to pi, we've made it all the way to negative I. And then by the time we make it to 3 pi over 2, we've made it to negative j. So what we see on this one is a counterclockwise circle that traverses the same graph. Well, I've got a counterclockwise, I've got a clockwise, so how is this one actually going to be different? Well, if we look at it, at the time 0, we start at I. So at time 0, we start at the same place as the second function. But by the time we make it to pi over 2, we actually make it all the way to negative j. So are we going clockwise or are we going counterclockwise? Well, it's hard to say. The next time around, we make it to negative I. So then we would make it to negative I. And then by the time we get to the 3 pi over 2, we make it to positive j. So the question then becomes, does it look like we're going clockwise or does it look like we're going counterclockwise? Well, that's kind of an interesting question. From the way you look at it, it looks like it's clockwise, but it's not actually so cut and dry. What you might want to do is take something simple. Take something like t equals pi over 3. So that's between 0 and pi over 2. So if we're going if we're going clockwise, then we should end up somewhere here in quadrant 4. But if I take R3 of pi over 3, I get cosine of pi I plus sine pi j. Well, sine of pi is 0. Cosine of pi is negative 1. So I actually end up over here at pi over 3. So what you're actually finding is this is just turning the clock counterclockwise, but it's doing it 3 times as fast. So, or 3 times as quickly. So when this one would normally stop here, this one turns all the way here. And so then at the next time it turns 3 quadrants, it turns here. The next time it turns 3 quadrants, it turns here. But if you don't plot with enough granularity, you actually would think it's going in a clockwise direction when in fact it's going in a counterclockwise direction. It's going in the same direction as the blue graph. And so what you're finding is that the difference between R2 and R3 here is this is sort of, you can think of that as like a speed, right? If I crank that value, it makes the graph go more quickly as time progresses. And so anyway, in terms of just space curves, that's the general idea. We want to split up each of these into individual functions and think about them behaving independently, because we're going to use that in this whole section to start defining interesting properties about graphs in multiple dimensions.